What we're trying to do is to say, okay, for all of the devices that have not been classified because we don't know these devices, the goal is basically to say, I will go to the user and say, I have a cluster of devices. I don't know what they are, but I know that they are identical. And there are many ways to say that if you have a multi-dimensional space, you want to group devices to say they all behave in the same way. For that, because we're running on top of DNA, we collect multiple attributes. The OUI, the CDP, and LDP, Krishnan mentioned that, but also GSTP, we have many, many parameters that we take. So now what do we do with that? The idea, and I'm sure you guys know machine learning clustering, at the high level, it looks very easy, right? You just think, well, if they are close to each other, then they must be similar. And 1 point in this example is equal to one device. But the reality is that the distance that you specify so that you can say these devices are close, so they are similar, is extremely complicated. I won't go there. If I had been given 2 hours, I would go through the math to explain a bit more. But we're using multiple mechanisms to find out the similarity level. So what the engine did at this stage is to say, you've got 5,000 devices that are unknown. I can tell you there are only 15 clusters. Now, Mr. Customer, could you give me a label for these guys? And because you're running on top of DNA, you have multiple attributes you can play with. I won't go there, but it's just to shed some light on the level of complexity to achieve that task. Because when you assess the efficacy of your system, you can look at the purity of the clusters. You can look at what we call the compactness. You can look at the number of clusters. And depending on how you tune your distances and the type of algorithm you're using, then you could come up with very different outcomes. We spent many months looking at the best compromise so that we can maximize the purity. You don't end up with similar devices in different clusters. You don't have too many clusters. You just have a few. And that's what makes this solution really appealing. So that was a part. And there was a good comment about YML. Well, in this case, you don't have any ground truth. You don't know what these devices are. So then now you can start grouping and say, I don't know what they are, but instead of flagging 5,000 devices one by one, you only have to give a label for 15 or so. Now, let's talk a little bit about the attack. So that's another very interesting point. You have a full spectrum of attacks, right, that can happen. It goes from max spoofing, which we know is not super hard to detect. You can really live with rules, that's just fine. If you find the same MAC address connected to 2 different ports at a given time, for example, well, it's not very hard to figure out that you have a max spoofing attacks. At the opposite side of a spectrum, you're going to have stealth watch. And this is for advanced malware. That's not the scope either. What we're doing with that product is to have something in the middle and cover many attacks such as probe spoofing or some kind of man-in-the-middle attacks. So why do you want to use ML for that? Because you need to look at the behavior. And what we mean by an attack in this case is an anomaly. And an anomaly in this particular case is the behavior of that device when I start to watch the device and what it does. Using NetFlow, for example, I can tell you that I've been trained, and we're using support vector machines and other algorithms to do that, that are trained to recognize a type of device. So if you pretend to be a voice over IP phone, but you're not acting as an IP phone, the classifier will be able to detect that and say, this guy cannot be a voice over IP phone. And that's why you need a ML in this case, because you cannot end up with a solution with just a rule, if you will. And I'll show you that in a minute. Hold your breath, you'll see that. What is the architecture? So let me explain real quick. We are training, the algorithm in the cloud, but the inference is done locally on-prem on Cisco AI, on the Cisco AI agent. So basically, it's a sort of one-way download of models being trained in the cloud, because back to your point about Wi-Fi and how we can cross-leverage data set, we're using a vast amount of data so that we train the best algorithm. Then they are used on-prem. And then what you do, we get the NetFlow, we're using NetFlow and other attributes, we run by the machine, and the machine learning algorithm says yes or no, and then we can compute the trust model. I just wanted to show you that one
Hey,
because
JP,
yeah.
how's this going to detect man-in-the-middle types of attacks?
Oh, yeah, you know why? Because, and actually that's great. That's exactly my next slide. Because in this case, you would detect that if you look at this case, right, you have A and B. If there's a man-in-the-middle attack, between the switch here and the MAC A, you will detect that there's a change of behavior. So because you know the behavior of MAC A, which is a printer, if you start exfiltrating some data, for example, you will detect that there's a new application never been used before, the type of traffic is not the same, the size of packets is not the same. So there are multiple attributes that will tell you that indeed it cannot be a printer. And that's why I wanted to show you that result real quick. We have many results like that, but in this case, we managed to get a very high precision and a very high recall as well. And if you guys want to discuss offline about the parameters and how we're using SVM and stuff like that, I'm super happy to talk to you about that. The other one is also about the probe spoofing. So you send a probe, whether it's a DHCP probe, for example, and then you start doing exploiting, for example, a threat. Here we just give an example. Well, you're going to find out this as well because we look at the behavior. And that's why we can detect fairly classic attacks like probe spoofing, but also man-in-the-middle attack. Does that make sense?
Yeah. Yeah,
So,
thanks.
So before you move on, so if I look at this model, how does this change as we go from large corporate infrastructure and corporate networks to more of a work from home model?
Yeah. So what we do, we have multiple ways of doing that. First of all, because the problem is that the environment in which you train your model must be removing the noise and be agnostic to environment as much as possible. And you're absolutely right. The way you do that is that you have multiple techniques to remove the background noise. So if you start detecting the behavior of a telepresence, for example, you need to have a way to classify it the same way as if you were running the telepresence in a home office. And of course, the environment in the background is very different. The behavior of a telepresence is the same. So there are techniques in ML to remove that kind of, it's not noise, but is over traffic that is running on top of the behavior of the device. That's what we do. And that's why we train, we do a lot of, we cross-check across data set and things like that.
But JP, does this mean that, so if I'm managing my corporate infrastructure and now my staff are beyond IT, my entire employee base is now working from home or a significant portion, does this mean that I'm going to have to move a device like that NetFlow exporter out to that edge within their network? Or am I going to have to backhaul the traffic all the way across the WAN back to my corporate infrastructure to be able to manage it? How's that going to play out?
Right. So for the NetFlow, in this version of the solution, you need to export NetFlow across the WAN, like what we do with StealthWatch, for example. In the future, we want to run the inference for east-west, for example, detection of attacks. We want to run the model on-prem, on the box, at the edge of the network. That's not what we're doing today. But we have designed the classifier so that they can run anywhere in the network, and you may not have even to send NetFlow.
So if I heard you right, I do need to backhaul all that traffic back to my corporate network.
The NetFlow traffic, only the NetFlow traffic.
Yeah, so a related question would be similar to that. This will work when you have a complete NetFlow or network flow under your control, as well as the applications, enterprise applications. Particularly, a lot of enterprise companies are moving to the SaaS model, which means you may or may not have control over that, and you may not be able to decide that in the SaaS application level. How does this work there?
So you need to have access to the information about the behavior of a device, obviously, right? And that's why, the day you have it on-prem, you don't need to export anything because you see the traffic going through, on the box itself. For now, it's very easy. Whether you do SaaS or not, you export the NetFlow and you push the NetFlow, in your data center where you're running that DNA center.
Okay, so the traffic flows through you first. You do that before you can send it. Okay, got it.
Yeah. All right. So I'll go quick about that. It's just to say that, I just wanted to run an experiment for you. just to show you, because at the end of the day, when you look at machine learning, right, it's a way to learn dynamically a rule, right? That's exactly what ML does in a highly multidimensional space. So I took one randomly. I wanted to show you what the rule would look like to detect, for a given classifier. And this is the size of the rule. So what you see on the right is similar to one of the classifiers that we're using. And you see that the rule would be having hundreds of entries. And that shows you that you cannot use such a rule to detect, this kind of attack in this example. So again, it's just to show an example, but and to be honest, if you can come up with a rule that is not too big, don't use machine learning. Now, if in order to accomplish a task, you need to come up with a rule with 200, entries, that's probably the right decision to use machine learning. But I just wanted to give you a quick example about that. Okay, let me show you what's coming next, because I think this is super exciting. So, I think that, and I want to give you a sneak peek, because as I said before, the journey started about 10 years ago. And we've gone through a long journey, and we have learned a lot of things. I can tell you many techniques, how to clean up the data set, how to remove noise. And we've done a lot of things there. It's our fifth product in this area. Now, when I'm looking at what's coming and the future of the WAN and the internet and SD-WAN and all those things, what I do believe personally is that we know that we live in a multi-cloud world. We know that we have a plethora of access, from DSL to fiber and 4G and 5G coming soon, and then you have multiple types of access, MPLS is internet with tunnels, with direct internet access. All of our customers say the same thing. They say it's all about application experience and security. And I do claim that it's extremely hard to achieve without, such a high dynamic environment, without deep analytics and machine learning, capable of predicting and automate. So I like to share with you one slide. And again, it would take much more time to go through every details, but I think this is still interesting to do it quick. If you look at, we looked at millions of paths. I'm not saying a few hundreds, but millions of paths across the internet with SD-WAN, MPLS, you name it. And we started to model the loss and the delay and other variables. I won't go through the statistical models, but what you see is that you have a range of values, even between the same pair of cities, depending on the SP, the region, the type of access. And that's true for loss, that's true for delay as well. Now, if you look at the SaaS applications, we know that the workloads, they keep shifting, and that's completely normal. So what that means is that the dynamics of the internet is extremely high. We knew that. The dynamics of the flows and the application is extremely high as well. And during the course of one day, we do see huge variation as well between a given pair of cities, for example, with the same SP. So you end up with SLA violation, you end up with a lot of things like that. Now, when you look at that, and if you really care about the application experience, in such an environment where you have such dynamicity, you have so many options, and the application keep moving, it's almost impossible to keep managing these networks with rules and you do your design and then you check and you look at you troubleshoot and then you change your mind. So this is really where we are going. I believe that in terms of challenges, where machine learning can help is one, complexity. And by the way, it's not Cisco, it's the world, right? We know that with SD-WAN, it gives you a great deal of flexibility. That's a great technology, a lot of pros. But at the same time, when you've got to configure your template to optimize the routing between MPLS and internet with tunnels, you can go to DIA or you can send to a cloud security provider like Umbrella. Then you have a lot of options, and it's difficult to do in a reactive way. The second piece, which I believe is very important for the future, and I would love to get your feedback as experts, is that these networks, they are fundamentally unpredictable for many reasons. And we can compare MPLS, internet, and 5G, and you name it. But that's a fact. And I believe ML can help dramatically reducing the level of unpredictability. And the last piece is that these networks, they're not optimized for application experience. We know that. Routing, as much as we love routing, as you know, and you guys too, I'm sure, You always do best path selection. You optimize for a given destination with constraints, without constraints, but not for the application experience. And I believe that ML can be a game changer, addressing one, the complexity, second, the predictability, and third, the user experience.